All right, let's dive into one of the biggest head-scratchers in electronics. Seriously, it's a paradox that seems to fly in the face of everything we know about circuits, and it stumps people all the time.
I mean, think about it. A capacitor is, by definition, an open circuit. It's a physical gap, an insulator, put there specifically to stop electrons from crossing. So how in the world does an alternating current, which needs a complete path, seem to flow right through it like it's not even there? Let's crack this thing open.
Okay, quick refresher just so we're all on the same page. A capacitor is basically just two metal plates with an insulator sandwiched between them. If you hook it up to a DC source, like a battery, what happens? It fills up with charge and then, bam, current stops. Dead end. It's an open switch, and that's exactly what you'd expect. But with AC, the rules are totally different.
Visit youtube.com/avidsystem and don't forget to subscribe.
Now, the first big clue to solving this mystery isn't hiding inside the capacitor. Nope. It's all about the very nature of alternating current itself. This is the sine wave's secret.
You see, DC is like a steady one-way push. It's predictable. AC, on the other hand, is constantly in motion. The voltage smoothly rises to a positive peak, gracefully falls back through zero, dips down to a negative peak, and then starts that whole beautiful dance all over again. And that rhythm, that's everything.
So how does our little capacitor deal with this constant wave of changing voltage? Well, it tries to keep up. As the voltage rises, electrons pile onto one plate, charging it up. But just as it gets comfortable, the voltage starts falling, and all those electrons rush back out. Then, the voltage reverses, and electrons get shoved onto the other plate, charging it with the opposite polarity. It's this never-ending cycle of charge, discharge, charge the other way, discharge, thousands or even millions of times a second.
And here it is. This is the big aha moment. Get this. Not a single electron ever actually jumps across that gap. It can't. But this constant shuffling of electrons, this back and forth sloshing on both sides of the capacitor, means that current is flowing everywhere else in the circuit. The effect of a current is there, even though the path is technically broken.
Okay, so we've figured out that current effectively flows. Awesome. But this whole process creates a really fascinating, kind of weird side effect. The relationship between the voltage that's doing the pushing and the current that's actually flowing, it gets knocked out of sync.
In a super simple circuit, say with just a resistor, voltage, and current, are best buddies. They're perfectly in sync, rising and falling together in lockstep. But the moment you swap that resistor for a capacitor, something strange happens. The current actually gets out ahead of the voltage.
And this leads us to one of the most fundamental rules you'll ever learn about capacitors. The current, the actual flow of electrons, hits its peak value a quarter of a cycle before the voltage does. We say that the current leads the voltage by 90 degrees.
And you know what? This actually makes perfect sense when you think about it. When is the rush of electrons going to be the absolute greatest? Well, it's going to be when the voltage is changing the fastest, right? And that happens right as the voltage sine wave is crossing zero. And when does the current stop? For just a split second, right at the peak of the voltage wave, when the capacitor is totally full and the voltage for just an instant stops changing. At that moment, the current is zero.
Okay, so we've got a current, and we know it's a little ahead of the voltage. But does the capacitor just let this happen? Does it put up any kind of a fight? Oh, you bet it does. And that opposition has its own special name.
A resistor's job is simple. It provides resistance. But a capacitor? It also opposes current flow, but it does it in its own unique dynamic way that only happens in AC circuits. We call this opposition capacitive reactance, and we shorten it to XC. It's literally the measure of how much a capacitor pushes back against that sloshing AC current. And here's the convenient part. Even though it's a totally different physical process, we measure it in the same unit we use for resistance, ohms. Now here's where it gets really cool. This opposition, this reactance, it isn't some fixed number. Not at all. It changes based on one critical factor, the frequency of the AC signal you're feeding it. And we have this simple but incredibly powerful formula that lets us calculate exactly what a capacitor's opposition is going to be in any AC circuit. This is the recipe, the key to understanding how it's all going to behave.
Let's just decode this real quick. XC is the reactance we're trying to find in ohms. And down in the denominator, the bottom part of the fraction, we have F, which is our frequency in hertz, and C, which is the capacitance value in farads. Pretty simple, right?
But here's the main takeaway, the one thing you absolutely have to remember from this formula. Because frequency F is on the bottom, it means there's an inverse relationship. As the frequency goes up, the reactance goes down. They always move in opposite directions. Here's a way to picture it. At really high frequencies, that voltage is whipping back and forth so fast, the capacitor barely has time to charge up before it has to discharge again. It can't build up much opposition, so it acts like an open door, really low reactance. But at low frequencies, it has all the time in the world to charge up fully and push back hard, acting much more like a wall, really high reactance.
Let's make this real. Let's take a common 220 nanofarad capacitor. If we send a 1 kilohertz signal through it, the math tells us it has a reactance of about 723 ohms. Okay, but now let's crank that frequency up by 20 times to 20 kilohertz. Look what happens. The reactance just plummets all the way down to about 36 ohms.
And you can really see that massive drop right here. We increased the frequency by a factor of 20, and the opposition decreased by a factor of 20. The capacitor basically becomes more and more transparent to the current as the frequency gets higher and higher.
And this all leads to a final, really powerful idea. If a capacitor acts like a gatekeeper that lets high frequencies pass through easily while blocking low frequencies, what does that mean you can build? This single principle is the heart of every audio filter, every equalizer on your stereo, and countless other circuits that shape our world. It's not a weird glitch, it's a feature, and it's one of the most powerful tools in all of electronics.
Thanks for watching.